Je vous propose d'écouter maintenant Hilke Plassmann, qui est à l'INSEAD, du côté de Fontainebleau, mais également qui a réalisé beaucoup de ses travaux à Caltech, en Californie, et elle va nous parler de Neural Correlates of Value Computations during Simple Economic Decision Making.
First of all, thanks a lot for having me. I'm very excited to be here today, and I would like to take this opportunity to thank the organizers to put together this great colloquium. I'm sure it will be an exciting day, and I hope I can contribute to that a little bit with my talk. What I'll talk about is the neural basis of decision value computations. And before I get into specifics of the studies I will present to you, I would like to explain you a little bit what I mean with decision value computations. So, and what I'll actually do is I will take a point of view from behavioral decision making, and so this is what Stan referred to. This is a work from Daniel Kahneman and Amos Tversky, and these are psychologists who received the Nobel Prize in economics a couple of years ago. And this is also part of the agenda in neuroeconomics to actually distinguish different value signals that are important for decision making. And so first of all, there is, how does that work? There's something what we would call predicted or value, or predicted, an economist would call it utility. And this means when you think about an object, how much your welfare would increase if you could have or consume this object. And then there's a decision-making context that kicks in where you have to trade off at least two different alternatives, and you have to compute a value to think about how much you would like to have this object. And then once you have decided, or once you have chosen, you will most likely consume that object. And this is what is referred to as experience value. And then after the consumption, next time before you are in the decision-making context again, you will have something like a remembered value. To make that a bit less abstract, let me show you what I mean by that. So here I have a nice Belgian chocolate bar, and now I need a guinea pig who I know has a sweet tooth. How much do you think this would increase your welfare, your happiness, to have this chocolate bar? On a scale from 1, not at all, to 7, a lot. 4. Okay, so I'll give you the chocolate bar. So this was kind of a prediction from Virginie about the value. So now what I'll do is I'll play a bit with her, and I have a Toblerone bar here. So, and I ask her, so would you be willing to trade in your chocolate bar for the Toblerone? No. Okay, so then she makes a clear decision. She's trading off the values. But now, and this is what I will be focusing on in my experiments, is I have something else. I have a more general good that has a utility for us, which is money. So can I buy back the chocolate bar from you for $3? Sure. Okay. All right, so that was a little demonstration of what I will be talking about today, which are decision value computations and how our brain is computing those values. So, and it's not something which is very abstract, it's actually something which all of us are computing in our everyday life, because this is pretty much what our world economy is based on. You can boil it down to these trade-offs we make on a daily basis when we go to eat food, when we have to choose from a menu. Here, when we are on the farmer's market, when we're on eBay or whatever, we have to think of how much something is valuable for us and how much our resources are we willing to trade in order to obtain this good. So in a very simplified model, you could think about that as there's an object and you compute a value for it. In a decision-making context, there are actually several of these objects. And what you need to do is you need to make a trade-off between these values. You have to assign so-called decision weights, and then what you'll do is you will select the item with the largest decision value, and then deploy the subsequent appropriate action. So, and this decision value computations is what I will be talking about today in my talk. And what I'll actually use as a measure for that is willingness to pay. With willingness to pay, I mean that how much resources in form of money or how much of a reward am I willing to give up in order to obtain another reward, for example, Toblerone. And this is important for very simple decision-making processes. So you see the object, you think how much are you willing to pay for it, then you compare it with a price in a given store, like at Carrefour, and then the result of this equation will actually lead to a yes or no purchasing decision. So, and the big question of all these studies I will present to you is there a specific system that tracks these decision value computations? And if so, how does that system relate to other neural networks underlying different value or utility concepts? And I will talk a bit about that. I will look at positive and negative decision value computations. So this is studies 1 and 2 of today's talk. And then there's other work from former colleagues of mine who have looked at differences between the decision values and the expected values. And you could do that for all of the other values I mentioned in the beginning. And this is relevant for me to understand because we know that when I ask people simply about that, I will always get different answers. And one idea to do this type of research is to understand whether we find differences in these concepts because we simply use noisy measures to sample them, or because they're really different mental constructs. And in the next steps, if there's really such a system where I can correlate brain activity with the behavioral measures, what is the causal relation here? So can I, via manipulating brain activity in this neural system, actually change economic preferences? And we know, and Stan was referring to that in his introduction, that we have these models about stable economic rational decision-making, which Kahneman and Tversky have proven not to be true. We know there's certain contexts when our economic preferences are not stable, where they are biased. And this is work I will, because I only have 40 minutes today, I can't present, where I look at, okay, what are different contexts and how does that bias the stable economic preferences. And then more recently, I've also looked at how can I train people actually to help to overcome these biases, and how can I help them to make better decisions in case I miscompute the decision values. So the first study is joint work with Jonah Doherty and Antonio Rangel. And this was the first very basic studies in the series of research where I looked at, is there actually a specific neural system that tracks appetitive decision value computations? With appetitive decision value, I mean positive decision values. And I use the word appetitive because I literally used the same stimuli I was just playing with Virginie, so I used food items. So the major question of this research was, is there a specific neural system that tracks decision value computations in an appetitive context? And the hypothesis we had here is that there is animal work, but also human fMRI work that has shown that there's a specific brain area in our prefrontal cortex, more specifically the medial part of the orbitofrontal cortex, that has been shown to be involved in preferences and choice situations. So our a priori hypothesis for this first study was that the higher the appetitive decision value, the higher activity changes in this brain area, the medial orbitofrontal cortex. And in order to investigate that, we asked 19 Caltech students to participate in what I call the junk food bidding task. So I recruited subjects that I screened for liking and occasionally eating junk food. And for all of those here in the audience who are actually from Caltech or who have been at Caltech at some point, know that it's not difficult to find these subjects at Caltech that like junk food. And the stimuli I used is pretty much the same thing as I've done with Virginie just a couple of minutes ago. I gave them, upon the arrival in the lab, I gave them 3 $1 bills. I told them, this is your money, you can either keep it or you can use it to buy certain food items from me. And one thing I haven't mentioned yet is that these people they were hungry because I asked them to fast 4 hours prior to the experiment so that the food items actually have a high incentive value for them. The food items I used were 50 different food items, and there were sweet and salty items like candy bars and chips and stuff. So the task was, there were so-called free-bid trials, so trials where people would see a food item, then they could tell me how much they want to bid to eat the food item, and these possible bids were either $0, $1, $2, or $3, and then they would receive a feedback. This was what I refer to as free-bid trials, but then there was, as a control condition, so-called force-bid trials. So this was it was identical, except that they were told what they need to bid during those trials. So they didn't have to do the computation, the value computation. And the idea behind that is to isolate really the computation I'm interested in here, which is the decision value computation. In order to make sure that subjects are really bidding their true subjective value, I employed a trick or a mechanism from behavioral economics called the Becker-de-Gucht-Marchak auction mechanism that makes sure that you don't over or underbid. I will show you how that works in a second, which has been well established in the literature as being a measure for true decision values. So what I ended up with as measures was, on the one hand, the bids as behavioral measure that I then could correlate as a real, like, on-time measure on the fMRI signal. That was my measure for the neural activity for the DV computation. So just one thing about the BDM auction mechanism. First of all, here is a crucial thing about the experiment is that I really have a measure that is on time. So on every trial, people would do the value computation. There have been other experiments in literature which have asked people afterwards for their preferences, but that's very different here because here I'm really interested in what's happening, how when people are doing the computation, what are the neural correlates, what are the underlying neural networks of that. So it was important to have this trial-by-trial measure for decision value, and then the rules were as follows. There were 2 urns, and at the end of the experiment, the subject would draw a number of each of these urns. One urn would have as many numbers as trials, and so the number would determine the trial, which is a trial that counts. The idea behind that is that the subject doesn't have to think about spreading the budget of $3 over all the trials, but every trial could be the one that counts. And then the other urn, there was the real price which was in there, so the bid was not the price, but the price was the number of the amount drawn from the other urn, and depending on the relation of the price, so the number drawn from that other urn to the bid, the subject would either get the food item at the end or not. This is very important for these types of experiments, that you're looking at non-hypothetical decisions. And so here it was really something for stake. They could either get the food item at the end, or they could keep the money. And again, these people were very hungry when they came to the experiment. The time course of the experiment was as follows. Subject fasted 4 hours prior to coming to the experiment. Then they were instructed and so forth. Then they would engage in the bidding task in the scanner. At the end, the auction was implemented. And then to make them even more hungry, or to increase the incentive value of the food items, we instructed them, you have to stay in the lab for another 30 minutes. And at this point, they were already really, really hungry. And you can do whatever you want. You can read a book. You can also eat. But the only thing you can eat is the food item you can buy from me. So regard me as your personal kind of convenience store for this experiment. And so if you would have been my subject, you would have seen the following screens. These are the free-bid trials. You would see a food item. Then you would be instructed to think of how much you want to bid for it. Then you would put in the response. You would get a feedback, and then an inter-trial fixation cross. Again, the force-bid trials were identical, except that here, instead of seeing a question mark, you would see a price that you would have to bid, that you don't need to think about how much you want to bid. This number would be repeated for the response. You get feedback, and so forth. So we had 50 trials of each, so a total of 100 trials. And what we found here with respect to the behavioral data It's pretty much more like a control. As you see, what we're interested in here is what is shown in light blue. So these are the bits. And what this shows me is, well, I was kind of successful in my manipulation that my subjects actually bid in over 70% of the trials a bid that was higher than 0. Now, when I look at the brain model I used, so just to make this part a bit shorter, this is the regression model. What I'm interested in is what's happening during the free bid trials at the item presentation, so when they see the item, modulated by their response. So it's a parametric regression model. And I was subtracting this condition from exactly the same condition when there was a force bid trial. So this allows me to really isolate the decision value computation. And what I find is, I actually find 2 brain areas being involved in the decision value computation. One was, according to my prior hypothesis, was the medial prefrontal cortex. But I also found another area, which you see here, which is the dorsolateral prefrontal cortex. And when I zoom in now into the medial prefrontal cortex, what I find is that really the brain activity or the change in the bold signal amplifies with the value. So here you see the $3 curve, you see $2 curve, $1 curve, the $0 curve, and it separates nicely after a point of time, and then it gets back together after a point of time. And this looks very different when you look at the force bid trials. The force bid trials, you can't see such a pattern. It's not separating. It's more random noise. So the conclusion of this first study is, well, there is a system that tracks decision value computations, and this system is actually the medial prefrontal cortex and the DLPFC, so the dorsolateral prefrontal cortex. And what that means is that in these brain areas, a variety of other input variables that are important for decision making are actually integrated into a single representation for appetitive decision values. And so for my overall research agenda, that might tell me that decision-making biases, what also Stan has referred to in his introduction, might work through maybe a modulation of these areas or connected areas. But what we were, to be quite frank, a bit puzzled here was, so what is actually the role of the DLPFC for these decision value computations? Because we had a strong hypothesis about the medial prefrontal cortex, but not about the DLPFC. In a second follow-up study, we looked at the area we found, or the 2 areas we found to be tracking the appetitive decision values, is it the same brain area, or is it the same underlying neural network that also is involved in aversive decision value computations? And there are different theories when you look in the neuroscientific literature that needs to be taken seriously about this question. So one set of results would suggest that it might be more like experience values, so positive and negative emotions, where we know that there are different underlying systems, so they're not represented in the same neural network. Then there's also work showing that there's frontal brain asymmetry, so maybe punishments are processed in brain areas in the right hemisphere as compared to the left hemisphere. Or, and here you could see what sort of our a priori hypothesis was, because this is a theory from one of my co-authors who found actually, well, it could be that it's more like a lateral versus medial kind of story, because John Doherty found that the magnitude of abstract punishments are represented in the lateral OFC as compared to abstract rewards that were shown to be encoded in the medial OFC. And then the last theory here is it could be that we have one general decision value system, and this is based on findings primarily from Sabrina Talmadal, which was published in Science in 2008. And they looked at financial decision making, and what they found is that losses are represented as deactivations in the same areas that trigger increased activation changes for gains. So in order to investigate the study, we again asked 19 Caltech students, and this time we screened them actually for disliking certain foods. The stimuli we used were baby food and canned meat. Just on a side note, what was interesting here is that I really, after some pre-testing with some of my other German fellow students, and at Caltech we also have a high Asian population. It was, for the positive food items, it was very clear what are positive food items. For the negative food items, that was not the case, because it seems like that, for example, the Germans and the Asians, they all like canned meat, whereas for Americans this is something which is disliked. So I had to actually screen out second-generation Americans for this study. The idea of the design is very similar. So again, people would come to the lab, they would receive 3 $1 bills they could use to bid on 50 different disliked food items. And they were also, again, sweet and salty. The main difference here is actually that they did not bid on their right to eat the item, but they bid on the right to avoid eating the item. So once they signed up, they kind of agreed that they would eat whatever food the auction mechanism would determine. The only possibility to get out of that is they can use the money to bid not to eat the food item. And then there were also force-bid trials. It's really very similar to the first experiment. And we used, again, the BDM auction mechanism to make sure that they bid their true decision value to avoid eating the item. And that is all the same. So also the design is very similar. For your convenience, I highlighted what's different. So here, what's the only thing which is different is that the subject actually ate 2 hours prior to the experiment. So the idea behind that is that they would come full and not hungry to the experiment, so that they really wouldn't be after eating one of these items. And also the trial structure is very similar. Here you see free bid trials, and there's the baby food. This is steak and carrots in mousse form. Free bid trials, identical to force bid trials, other than that here is again the price. And what we found with respect to behavior results, also similar to before. Again, what's interesting is in light blue, the free bids from the free bid trials. In over 70% of the trials, subjects actually bid more than $0 in order to avoid eating the food item, which is a manipulation check to see that we have enough variance to run our analysis. Also, another control check here is at the very end, we actually sampled also liking ratings of the food items. And what we see here is a significant negative correlation. So it really is that the bids reflect disliking of the food items. And what we found is when we looked at what are brain areas that correlate positively with the decision value, so the same analysis we did before was kind of disappointing because we couldn't find anything. But then we switched the sign, and when we looked at what brain areas actually correlating negatively with decision values, we found 3 areas: the bilateral medial-orbital frontal cortex, the bilateral dorsolateral prefrontal cortex, and also, interestingly, the right posterior insula. And then when we look at what is actually happening when I subtract the free from the force bid trials, it's again the bilateral medial-orbital frontal cortex and the bilateral dorsolateral prefrontal cortex and the left insula. So that means that in the force bid trials, again, there's not much going on. All the results I showed you on the slide before were driven by the free bid trials. And what is interesting is that, so the left insula is actually a bit counterintuitive because people have found the anterior part of the insula to be correlating positively with disgust and these kind of things. So that was a bit of a surprise, but again, it's a posterior insula, it's not the anterior insula. But these here are actually, when I overlap the results from study 1 and study 2, there's a huge overlap between these areas, which I still find very amazing that they overlap so much. So in yellow, you see the results from the first study, positive correlation with decision values, and in red, you see the results from the second study, where you had negative correlation with the decision values. So what that tells us is that aversive decision values correlate negatively with activity changes in the medial frontal cortex and the DLPFC. And these are the same brain areas I found to induce increased activity changes during appetitive decision value computations in study 1. So in other words, this underlying neural network is integrating for positive and for negative decision value computations into one single representation of decision value independent from valence. So this supports the view of one general decision value system. And this also shows, and this is interesting when you think back of what I showed you in the beginning, the different value signals. This shows that the decision-making context is actually different from, for example, the experience value context, where we know we have different systems. Because here it seems to be something very specific about the decision-making context, that we have one general system that is computing both positive and negative values. Still a puzzle here is the specific contributions of the DLPFC and the medial prefrontal cortex in computing decision values. So in a third study, what I'll show you is actually this also two studies, so study 3 and study 4. My collaborators and I, this time there are much more collaborators. One of them is actually sitting in the audience, Colin. We looked at what is the specific role for decision value computations of the DLPFC. And what we did here is we actually manipulated brain activity in the DLPFC using transcranial magnetic stimulation, or short TMS. And the idea here was, so is there, other than only a correlational relationship between these brain areas, is there also a causal relationship? And what our priori hypothesis is that if there would be a causal, or if there would be, if the DLPFC plays a necessary role for the decision value computations, then the application of inhibitory TMS in the right DLPFC as compared to control conditions should actually decrease my behavioral measure of decision value, so it should change my bits. And we had even a more specific hypothesis on that. It should actually, when you regress, a measure that is unbiased, so a measure that you sample before TMS, and you compare that with a measure that you, a biased measure that was sampled after TMS, then when you regress the biased on the unbiased measure, that it should actually change the slope, so it should down-modulate the decision value. And so the study design here was that we had a between subjects design. We had here we had to, in order to make sure that the results are robust, we actually had two groups that are very similar that received repetitive TMS on the right DLPFC, and we compared it with two different control groups. One group was an active sham, so it was also TMS simulation, which was done on the vertex. So this is an area that is often used in TMS studies as a control condition because there should be nothing going on. The other control condition we used was an inactive sham, so it's kind of a placebo treatment. Everything's the same. You have a coil and all these kind of things, but there's actually a metal plate in the coil so that no stimulation is actually done, but subjects think there is a stimulation done, and that was also done on the same over the same part of the brain as the treatment condition. So the design you're by now familiar with, I guess. So again, subjects receive $3 $1 bills, and they can bid it on 50 different junk food items. Here, so we looked at only the positive versions. We looked at appetitive decision values. The idea of the task is very straightforward. We had two parts, where the first part where we would sample an unbiased measure of decision values. So we asked them, how much would you enjoy eating the food items at the end of the experiment? And then after receiving the TMS treatment, we would do the BDM task, so the task we have seen in the other experiments before. And this was our biased measure of decision value. With biased, I mean that was after the application of TMS. And so this is that in a visualized form. We again asked them to fast for 3 hours. The first part was the liking rating part, then the TMS was applied, and then we would sample the BDM auction, so we would sample the biased measures of decision value. And we determined the target localization based on the results of the very first study. So we took the coordinates, wrapped them into the each individual space, And we tracked that or did this using a neural navigation system. So that's an optical sensor system where you can track where specific areas are with the help of a computer. And it's the same system that's used for neurosurgery. And here you see now the other co-authors. This is Mikhail, the first author, and this is Antonio Rangel, where we played around with the equipment. And so you see this is a coil, figure of 8 coil, and the coil is positioned tangentially to the scalp in a 45-degree angle. And we used a repetitive TMS train, which lasted for about 15 minutes. And so, again, the inactive sham, it looked really the same. It's literally the same coil, but the difference is that here is a metal plate in there so that there's no magnetic stimulation going on. And what we find here is, doing a regression analysis, first of all, what's interesting when we look at these bars here is that between the two treatment conditions, there's no significant difference when we look at t-tests between the slopes. So these are the slopes of the regression analysis. We find no significant differences between both treatment conditions, so the RDL-PFC1 and RDL-PFC2. And we also don't find significant differences between the two placebo or sham conditions. So this shows that our results are very robust. But what's interesting here is that we do find differences in the slope of the regression of the unbiased decision value on the of some of the bits on the liking ratings. We find that when I do t-tests with the slopes, we find that there are significant differences between the treatment and the control conditions, no matter at which one I look. So the vertex and the radial PFC and also the sham radial PFC, meaning that the slopes here they're lower for the treatment as compared to control. That means that we down-modulated, and this is what our hypothesis was, the behavioral measure of decision values. So, and then a very intuitive explanation for this results could be, well, it could be knowing what the DLPFC is doing. It could just be that people are not able to do number computations anymore. So in a control study, what we did is we looked at what's happening when people have to perform before and after TMS numerical computations which are not linked to valuations in a decision-making context. So what we did is we had two groups. One received RTMS of the right DLPFC, the other one receives RTMS on the vertex. And we had, again, 50 different junk food items, sweet and salty. The difference here is that we asked them to guess the caloric content. The measure before TMS was on a scale from 1 light to 6 heavy. And then the post-TMS measure was also guess the caloric content, but the scale was different, was on a scale from 100 calories to 600 plus calories. Same idea, calorie guess before, RTMS, calorie guess after. And what we find here is actually when we look at, again, the differences at t-test over the slopes between the two groups, we find no significant difference between these slopes between the two groups. And what that shows us is that activity changes in the lateral prefrontal cortex play actually a causal role for behavioral measures of decision values, but not for other non-valuation numerical computations. So this is a very interesting finding, but it's kind of raises some more questions than it actually answers, at least to my flavor. So the next question would be, so how does what happens actually when we combine this TMS experiment with fMRI? This is a study which is undergoing. We don't have the results yet, so we can see what does actually when I inhibit with TMS activity in the DLPFC, what happens to the activity in the medial frontal cortex? What is the connectivity between those areas? And then the other question is, so when the DLPFC plays such a necessary role for DFCL, for decision value computations, what is actually done by the medial prefrontal cortex. In order to investigate that, my courses and I are right now doing a patient study where we have lesion patients that have lesions in the medial prefrontal cortex and in the DLPFC. Also, when you think of what the DLPFC is doing, it has primarily been shown to be involved in executive control, cognitive load. Does it mean that maybe sometimes we have unstable economic preferences because of the DLPFC is engaged in different contexts in activities that actually biasing my stable economic preferences? And could it also be that maybe we have individual differences with respect to the decision value computations because we have different cognitive capacities that then at the end of the day modulate stable economic preferences, which could be a reason why we don't act as the Homo economicus, that is why we have sometimes irrational behavior and unstable economic preferences. And I would like to thank my co-authors and you for your attention.
Yes, I think we have time for a few questions. It's also the goal of the seminar to have questions.
Yeah, okay.
Thank you very much, Hilke, for a beautiful presentation. Jean-Pierre Changeux has another question.
I'm just continuing on the question that Stanislas raised at the beginning. You are just demonstrating that you have change in some region of the brain as far as the average activity is concerned. It doesn't mean that other regions of the brain are not involved. And my question is, do you have studied the same test with patients with brain lesions, or used any other kind of way, like EEG or whatever, that would assess that, in fact, the region that you are looking at are, in fact, crucial for the test that you are using?
So thanks for the question. Just to clarify, what I did in the first two studies was it was a parametric design. So I looked at which brain areas are kind of amplifying with the behavioral measures. So which brain area, the higher the bit, the higher the brain activity or the change in brain activity in that area. And to answer your second question, yes, we're right now collecting patient data, and the preliminary results look like that both. So we have a couple of different patient populations. Importantly, here we have BMPFC lesion patients and DLPFC lesion patients. And as compared to control, both of them have a very biased pattern of behavioral pattern of this decision value computations, but in a very different way. So one is more random, and one is they only bit zero. So it seems that the DLPFC and the MOFC do have very specific roles, but I can't. We are still running this study, so. But it's important that you, for sure, that you apply like different methods, because I mean the problem with fMRI, it's nice to localize, but then it's a pure correlational measure, and in order to prove a role of a brain area, I totally agree with you. You need to use another method, such as TMS we've used here, or use patients to really show, well, this area is crucial for this kind of computation.
If I may ask a question myself, even after the proof of causality due to the TMS study, there could still be several interpretations, as you noted, and I suppose they could be divided into two big categories. Either the dorsolateral prefrontal cortex interference interferes with the actual measure of value itself, or it interferes with the process of using these values to guide the decision. And the latter would fit with the idea that frontal cortex patients are often still able to give a cold evaluation, but yet they cannot take the right decision. They show a form of indifference to their own decisions. So I was wondering whether you had evidence one way or the other. For instance, if they were just able, without any choice, just to give a numerical rating of the price of these items, would they not be just fine?
Yeah, so I mean, so what the patient data suggests here is, and again, this is preliminary, is that the DLPFC might be doing exactly what you're suggesting in your second theory, that's delivering kind of the input, whereas the medial prefrontal cortex is doing the evaluation part. Because they bit zero, the MOFC patients, they bit zero, but the DLPFC patients, they bit a random pattern. So it seems it is input delivered. But yeah, so it's a very good question. Thanks.
I think we have to move on so that we don't lose. Thank you so much, Hilke, for this very
and who wants
exciting introduction. The candy bars will be for the pause. Thank you very much.